Hi guys, so today we will be jumping into looking at sample means. For the past week or past section, I guess, we looked at sample percents. And so I think you'll notice some similarities, but also there's a few important differences that I'll make sure I point out. Remember, in this unit, we are assuming we know everything about the population, but then we are also just pulling a sample from that population. And so, if you think back on what we studied in 5.2, we studied sample proportions, which arise most often when we're interested in qualitative or categorical variables. However, when we record quantitative variables, we're interested in means, right? Because we've got numerical data that we can actually calculate the mean for. So for example, let's consider the mean household earnings for samples of size 100. Here we've got the population distribution on the left, so all households in the whole population, and then the sampling distribution on the right. Okay, we're going to go down and compare shape, center, and spread for all three. Okay, if we look at this graph on the left, we can see that the majority of the data points are here on the, there we go, sorry, are here on the left, but we've got a tail, so our shape is skewed to the right. Right, our tail is on the right. Whereas over here, our sampling distribution, we've got a very symmetric shape. Remember, this sample is a sampling distribution with samples of size 100. So we repeated this sampling process over and over and over. And every data point represents the average household income for samples of 100. The center value here is pointed out at the mean. So maybe we'd say it'd be about $75,000. And then here it falls about at that same place. So if you're pulling from a population, you're going to get very similar center values. And then the spread. Obviously here we've got a much larger spread because we've got the lowest household earnings and the highest, right? We've got every value represented. So we go basically, it looks like from 0 to maybe $250,000. So the range is $250,000. Whereas over here in our sampling distribution, we go from maybe $50,000 to $100,000, and that's because these are means. So we are sort of combining our data in a way that cancels out the lowest and the highest and settles sort of right in the middle. So our spread here, we go from 50 to 100,000. So the range is only $50,000. All right, so let's start noting some things about all sample means. If we choose many simple random samples from a population, then the sampling distribution of the sample mean is centered at that population mean, which is what we saw. Remember, our center values were aligned. They were at the same place. And then our standard deviation is found using this formula. So you take your population standard deviation and you divide by the square root of n, which makes your sample standard deviation much smaller than the population standard deviation, which is what we saw here. Remember, our range was significantly smaller than the population range. All right, this is where the central limit theorem comes in. So it says that if our sample size is large enough, then the distribution of sample means is very close to normal. And that's exactly the definition of the central limit theorem. So when, n is large, the sampling distribution becomes normal. And that is no matter what shape the population distribution had, right? So remember, up here in our example, we had a very skewed population distribution, but we took samples that were quite large. N was 100, and therefore we got a symmetric sampling distribution. All right, now how large that sample size is sort of depends. We're going to talk about that specifically here in a second. But here's another example, young women's heights. So the height of young women follows a normal distribution with a mean of 64.5 inches and a standard deviation of 2.5. So here in the purple is our population distribution. That is all young women. Whereas here in the blue is the sampling distribution. Notice their center values are the same. They are both the mean. However, notice the range of the blue, the sampling distribution, is much smaller than the range of the purple. And that's because you have calculated all those extreme values to find your means. And so we don't know the shortest and the tallest. We just know those averages, right? Remember, sigma over the square root of n. So we get smaller because we divide by that square root of n. All right, now here is a really bizarre population distribution right here. We've got 3 different groups of data. It's really strange. Now notice from here we did a sampling distribution where n was 2. Here n is 5, 10, and 25. Okay, now describe the shape of the sampling distribution as n increases. So here, notice they started gathering closer together, but still had separate chunks. That was here in n equals 2. Here, all of the data sort of became one big group, but it was still sort of different peaks with a large standard deviation. Here, we're getting more symmetric, and here's the most symmetric. So as n increased, the shape became symmetric, right? And this is the central limit theorem at work. As n increases, our shape for any really bizarre population, our shape for our sample distribution becomes more and more symmetric. Now here's the normal condition. Here's what we need to know. If the population distribution is normal, that's a really important statement. If our population is normal, then any sampling distribution will also be normal. So we don't have to test anything. If it says your population is normal, then your sample is normal. However, if the population is not normal, the central limit theorem tells us that the sampling distribution of your sample means x bar will be normal if n is greater than or equal to 30. Okay, so let's put this to work. The customer care manager at a cell phone company keeps track of how long each helpline caller spends on hold before speaking to a customer service representative. He finds that the distribution of wait times for all callers has a mean of 12 minutes with a standard deviation of 5 minutes. And the distribution is moderately skewed to the right. So that's the population is moderately skewed to the right. Suppose the manager takes a random sample of 10 callers and calculates their mean wait time. What is the mean of the sampling distribution of x? So the mean of our sampling distribution, our sample means, will be equal always to the population mean, which was 12 minutes. All right, then the standard deviation, is always equal to that population standard deviation over the square root of n, which is 10. All right, let me get my calculator. Okay, 5 over the square root of 10 is 1.58 minutes. All right. Then, do you know the approximate shape of this sampling distribution of x? If so, describe the shape and justify your answer. If not, explain why not. Well, we know that the population was moderately skewed to the right. Okay, we also know that our sample size was only 10. And so 10 is not high enough to pass the normal condition. So we don't know the shape. Right? And that's because the population was skewed. So maybe the sample will be skewed. And n was 10. 10 is less than or equal to 30. So it doesn't pass the normal condition. All right, moving on. At the Nutty Peanut Company, dry roasted shelled peanuts are placed in jars by a machine. The distribution of weights in the bottles is approximately normal, with a mean of 16.1 ounces and a standard deviation of 0.15 ounces. Without doing any calculations, explain which outcome is more likely: randomly selecting a single jar and finding the contents to weigh less than 16 ounces, so less than the mean, or randomly selecting 10 jars and finding that their average contents weighs less than 16 ounces. And so let's think about this. If a jar, any jar, weighs less than 16, then it is smaller than average. Okay? Is it more likely that we'd choose one jar that happens to be smaller than average, or would it be more likely that we'd find 10 jars, find their overall average, and find that all 10 jars averaged out to be lower than the average? Okay? Hopefully in your head you're thinking it will be more likely to have just one jar weigh less than 16 ounces. Now this says find the probability. So we know that the distribution is approximately normal. So we know our population for all our sample means will also be normal. Okay, so we don't have to prove that. Now we want to find the probability that X bar is less than 16 when n is 1. And we want to find the probability that X bar is less than 16 when n is 10. Right? And so to find a probability, we're going to use n, normal n CDF. Here we're going from negative 1,000 to 16. Right? Remember, the mean for any sample distribution of means is equal to the population, so 16.1. And the standard deviation will be equal to the population standard deviation divided by the square root of n, which in this case is 1, so that stays 0.15. Okay, now over here, that standard deviation will be smaller because our sample size is bigger. Square root of 10. .047, so we'll say 0.05. Okay, now I'm going to plug these in my calculator. Second bars, normal CDF. Okay, so for one jar, this is a 25% chance, 0.25. 10 jars, this is a 0.022%. Much more likely if we only take one jar than if we were to take 10. All right, and then 4. Suppose that the number of texts sent during a typical day by a randomly selected high school student follows a right-skewed distribution with a mean of 15 and a standard deviation of 35. Assuming that students at your school are typical texters, how likely is it that a random sample of 50 students, so n is 50, will have sent more than a total of 1,000 texts in the last 24 hours? Well, first of all, let's notice here that our distribution is skewed to the right. Okay, and so we have to prove why our sample will be normal. And it will be normal using that normal condition because 50 is greater than or equal to 30. All right, so that opens the door for us to use normal CDF in order to find this probability. We know that the mean, will be equal to the population mean, 15, and the standard deviation will be equal to the population standard deviation, 35, over the square root of 50 students. Which is 4.95. All right, now, so let's think about this. We're looking at our distribution centered at 15. We want to know the probability that a random sample of 50 students will have sent more than 1,000 texts. Okay, well, let's think about this. If I put 1,000 here and my standard deviation is only 4.95, that's like going to come back to be 0. But that's because that's a total of 1,000. So we want to divide that 1,000 by the 50 students to put it in a per student format. So that's 20 texts per student, and it is more than that. All right, so now we're doing normal CDF from, not 15, 20 to 1,000. 15, 4.95. We get 0.1562, so 15.62%. All right. Okay, so now that leaves us off at this exit ticket. We have 3 problems, 6 total. Okay, see what you can do, and we'll see you next time.